Now let us consider another problem as per which there is a signal x of t given as sine cube of t. Please note that sine cube of t is periodic. We have to find the alternate Fourier series expansion of sine cube of t. So we know that the given signal sine cube of t is periodic with a period 2 pi. This can be obtained from the plot. So we have to, for finding the Fourier series expansion of sine cube of t, we have to get it in terms of sine of at and cos of at, where cos of bt, where a comma b belongs to z. So we can write sine cube of t. We can obtain this Fourier series expansion of sine cube of t by using the alternate fs formula. Now let us look into another way in which the Fourier series expansion of sine cube of t, the alternate Fourier series expansion of sine cube of t, that is by using the properties in the trigonometry. We know that sine of 3t is equal to 3 sine t minus 4 sine cube t. So upon simplifying this to get sine cube of t on left hand side, we see that sine cube of t is equal to 3 by 4 sine t minus 1 by 4 sine of 3t. From this we see that the alternate Fourier series expansion of sine cube of t by using the formula in trigonometry is 3 by 4 sine t minus 1 by 4 sine 3t. Please note that this is a valid Fourier series expansion because it contains the terms sine at and cos bt, where a comma b belong to z. Now let us consider another problem as per which there is a continuous time non-periodic signal which is conjugate symmetric. So say that signal is x of t. It is given that Fourier transform of dn by dtn of x of t is purely imaginary. Then find the condition on n for these conditions to be satisfied. Please note that as x of t is conjugate symmetric, x of j omega, that is Fourier transform of x of t, is real. So from this we can say that Fourier transform of dn by dtn of x of t is equal to j omega whole power n multiplied by x of j omega. But it is given that this Fourier transform is purely imaginary. We know that x of j omega is real, and so for the j omega whole power n x of j omega to be purely imaginary, j omega whole power n should be purely imaginary. So that implies n is odd. From this we see that if x of t is conjugate symmetric, for Fourier transform of dn by dtn of x of t to be purely imaginary, n should be odd. Now let us consider another problem as per which there is a continuous time non-periodic signal x of t given, where Fourier transform of x of t is equal to x of j omega. It's also given that Fourier transform of y of t is equal to x of j multiplied by omega minus 2. We have to find the relation between y of t and x of t. From Fourier transform of y of t, we see that Fourier transform of y of t is equal to y of j omega is equal to x of j multiplied by omega minus 2. Here we see that in frequency domain, y of j omega is obtained by shifting x of j omega by 2. So we know that shifting in frequency domain is equivalent to multiplication in time domain, so which can equivalently be written as y of t is equal to x of t multiplied by something. Now we have to find the factor by which we do that multiplication. We know that shifting by a in frequency domain is equivalent to multiplication by e power j at in time domain. So we see that y of t can be written as x of t multiplied by e power j to t. So from this we can say that y of t is obtained from x of t by multiplying x of t by e power j to t. Now let us consider another problem as per which Fourier transform of a discrete time non-periodic signal x of n is given as x of e power j omega, where x of e power j omega is plotted as shown. We see that the x of e power j omega is 1 in the range of minus omega c to plus omega c, and it is 0 in the remaining range of minus pi to pi. We have to find x of n from the given x of e power j omega. We know that from the synthesis formula, x of n can be written as 1 by 2 pi integral minus pi to pi x of e power j omega multiplied by e power j omega n d omega. So, which upon simplification becomes 1 by 2 pi, or sorry, which upon substitution for x of e power j omega becomes 1 by 2 pi integral minus omega c to plus omega c e power j omega n d omega. So, by performing the integration, this can be simplified as e power j omega n divided by jn divided by sorry jn, and the limits are omega c and minus omega c. So this upon simplification becomes e power j omega cn minus e power minus j omega cn divided by 2j multiplied by pi n. But we know that e power j omega cn minus e power minus j omega cn divided by 2j is equal to sine of omega cn. So x of n is equal to sine of omega cn by n. From this we can say that a low pass filter with a cutoff frequency of omega c is equivalent to time domain response of sine omega cn divided by pi n, or given any low pass filter whose impulse response is sine omega cn divided by pi n, the cutoff frequency is implied as omega c. Now let us consider another problem as per which there is a signal y of t which is derived from another signal x of t as x of t minus 2 divided by 3. It's given that Fourier transform of x of t is x of j omega, and Fourier transform of y of t is y of j omega. Now we have to find y of j omega in terms of x of j omega using the given relation. So from this we see that Fourier transform of y of t is equal to integral minus infinity to plus infinity y of t e power minus j omega t dt. So this can be simplified as integral minus infinity to plus infinity x of t minus 2 divided by 3 e power minus j omega t dt. So substitute t minus 2 by 3 is equal to p. From this we can write that t is equal to 3p plus 2. Also dt is equal to 3 times dp. From this we can write Fourier transform of y of t as integral minus infinity to plus infinity x of t multiplied by e power minus j omega multiplied by 3p plus 2 d omega. So this can be simplified as, sorry, 3 dp. This can be simplified as 3 times e power minus j2 omega multiplied by integral minus infinity to plus infinity x of p multiplied by e power minus jp multiplied by 3 omega dp. We know that the quantity marked, that is integral minus infinity to plus infinity x of p e power minus jp 3 omega dp is equal to x of j3 omega. So we can write the Fourier transform of y of t as 3 into e power minus j2 omega multiplied by x of j3 omega. So if y of t is equal to x of t minus 2 divided by 3, we can write that y of j omega is equal to 3 into e power minus j2 omega multiplied by x of j3 omega. Now let us consider another problem as per which there is a signal x of n given as shown in the figure. X of n takes a value of 2 at the instant 0. It takes a value of 1 at the instant minus 1. It takes a value of half at the instant minus 2. It takes a value of 1 at the instant 1, and it takes a value of half at the instant 2. So this is signal x of n. It's given that there is a derived version of x of n which is given as y of n is equal to x of n by 2 minus 1 if n is even, 0 if n is odd. So here we have to find the Fourier transform of y of 2 of n. So for finding the Fourier transform of y of 2n, first of all we have to deduce y of n from the given x of n. Then we have to deduce y of 2n. Then we have to deduce Fourier transform of y of 2n. So here we can see that y of n is equal to x of n by 2 minus 1 is obtained from x of n by delaying x of n by one sample and then expanding along time axis by 2. So from this we can write y of n as shown in figure. Okay, first of all we know that x of n is half comma 1 comma 2 comma 1 comma half, where the value of 2 corresponds to the instant n is equal to 0. By delaying the same by 1, we get the signal as half comma 1 comma 2 comma 1 comma half, where the first one corresponds to the n is equal to 0. This is actually x of n minus 1. Now by expanding the same by a factor of 2, we get the signal as half comma 0 comma 1 comma 0 comma 2 comma 1 comma half. So here we see that the value of 1 corresponds to the instant and is equal to 0. Sorry, there should be zeros inserted here. Now this is actually y of n. We know that y of 2n can be obtained from y of n by compressing y of n along time axis by 2. So if we compress the obtained y of n by 2, we get the signal y of 2n as half comma 1 comma 2 comma 1 comma half, where the value of 1 corresponds to the instant n is equal to 0. Now we have to find out the Fourier transform of y of 2n here, which can be written as sigma n equal to minus infinity to plus infinity y of 2n multiplied by e power minus j omega n. So this can be simplified as half e power j omega plus 1 plus 2 e power minus j omega plus e power minus j2 omega plus half e power minus j3 omega. By taking 2 common out, by taking e power j omega minus j omega from this, Fourier transform of y of 2n can furtherly be simplified as e power minus j omega multiplied by half e power 2j omega plus e power j omega plus 2 plus e power minus j omega plus half e power minus 2j omega. So that is equal to e power minus j omega multiplied by 2 plus 2 cos omega plus half multiplied by 2 cos 2 omega. This can furtherly be simplified as e power minus j omega multiplied by 2 plus 2 cos omega plus cos of 2 omega. From this we see that the Fourier transform of y of 2n is e power minus j omega multiplied by 2 plus 2 cos omega plus cos 2 omega. Now let us consider another problem as per which there is a signal x of n given as 1 comma 1 comma 0 comma 5 comma 1, where the value of 5 corresponds to the instant n is equal to 0. It's given that Fourier transform of x of n is equal to x of e power j omega. We have to find the value of integral minus pi to pi x of e power j omega d omega. We know that from the synthesis formula to get x of n from x of e power j omega, x of n can be written as 1 by 2 pi integral minus pi to pi x of e power j omega multiplied by e power j omega n d omega. Upon substituting n is equal to 0 in the above relation, we get that integral minus pi to pi x of e power j omega d omega is equal to 2 pi into x of 0. But we know that x of 0 is given as 5. So this is equal to 2 pi into 5, that is equal to 10 pi. So for the given x of n, we see that integral minus pi to pi x of e power j omega d omega is equal to 10 pi. Now let us consider another problem as per which there is a signal x of t given as 1 for minus 1 less than or equal to t less than or equal to plus 1, 0 otherwise. It's given that Fourier transform of x of t is equal to x of j omega. Here we have to find a value of omega for which x of j omega is 0. We know that x of j omega can be written as integral minus infinity to plus infinity x of t multiplied by e power minus j omega t dt. Upon substituting for x of t, we get that integral minus 1 to 1 e power minus j omega t dt. So upon simplifying the integral, we get that e power minus j omega t divided by minus j omega, and the direct integration limits are 1 to minus 1. So this can further be simplified as e power j omega minus e power minus j omega divided by j omega. So this can be written as 2 sine of omega divided by omega. This is because of the reason that sine t is equal to e power jt minus e power minus jt divided by 2j. It is given that x of j omega is 0. That implies 2 sine omega divided by omega is equal to 0. That implies omega is equal to k times pi, where k belongs to z. From this we see that for integer multiples of pi, x of j omega is 0. Now let us consider another problem as a part of which there is a continuous time non-periodic signal x of t given. It has a Fourier transform of x of f. We have to find the inverse Fourier transform of capital X of 3f plus 2. We know that given a signal x of t and the corresponding Fourier transform x of j omega, we know that x of t can be written using the synthesis formula as 1 by 2 pi integral minus infinity to plus infinity x of j omega e power j omega t d omega. Upon substituting omega is equal to 2 pi f, we see that d omega is equal to 2 pi times df. So we can simplify the synthesis equation as x of t is equal to 1 by 2 pi integral minus infinity to plus infinity x of j 2 pi f e power j 2 pi f t df multiplied by 2 pi. So this finally boils down to integral minus infinity to plus infinity x of f. This is upon writing x of j 2 pi f as x of f g power j 2 pi f t df. Now we have to find the inverse Fourier transform of capital X of 3f plus 2. Let it be y of t. From this we can write that y of t is equal to integral minus infinity to plus infinity x of 3f plus 2 multiplied by e power j 2 pi f t df. Substitute 3f plus 2 is equal to p. From this f is equal to p minus 2 by 3 and df is equal to dp by 3. From this we can write that integral minus infinity to plus infinity capital X of p e power j 2 pi t multiplied by p minus 2 divided by 3 dp by 3. This can further be simplified as 1 by 3 e power minus 4 pi jt divided by 3 integral minus infinity to plus infinity x of p multiplied by e power j into 2 pi pt divided by 3 dp. So this can be written as 1 by 3 multiplied by e power minus j 4 pi t divided by 3 x of t divided by 3. From this we can see that the inverse Fourier transform of capital X of 3f plus 2 can be written as 1 by 3 e power minus j into 4 pi t divided by 3 multiplied by x of t by 3. Now let us consider another problem as a part of which there is an input x of t given to a system which is LTI system to get an output of y of t as y of t is equal to zero point 0.5 multiplied by x of t minus td plus capital T plus x of t minus td plus zero point 0.5 times x of t minus td minus capital T. Now we have to find the filter transfer function x of omega of such system. We know that by taking Fourier transform on both the sides for the given relation, we get that Fourier transform of y of t is equal to zero point 0.5 times Fourier transform of x of t minus td plus capital T plus Fourier transform of x of t minus td plus zero point 0.5 times Fourier transform of x of t minus td minus t. So right side can be simplified as zero point 0.5 times. We know that x of t minus td plus t can be written as x of t minus of Td minus capital T. So Fourier transform of this quantity becomes e power minus j omega multiplied by Td minus capital T multiplied by Fourier transform of x of t plus, similarly we can simplify Fourier transform of x of t minus Td as e power minus j omega Td multiplied by Fourier transform of x of t plus 0.5 times e power minus j omega multiplied by Td plus capital T multiplied by Fourier transform of x of t. We know that the system function can be written as h of omega is equal to Fourier transform of y of t divided by Fourier transform of x of t, which can be simplified as e power minus j omega t as a whole multiplied by point sorry 1 plus 0.5 times e power minus j omega capital T plus e power j omega capital T. We know that e power minus j omega capital T plus e power j omega capital T can be written as 2 cos of omega t. From this we can simplify the system function as e power minus j omega td multiplied by 1 plus cos of omega t. So the system function which is h of omega is equal to Fourier transform of y of t divided by Fourier transform of x of t can be written as e power minus j omega td multiplied by 1 plus cos omega t. Now let us consider another problem as a part of which there is a signal x of n given as 1 by 3 whole power n u of n, sorry, 1 by 2 whole power n u of n. There is a derived signal y of n from x of n as y of n is equal to x square of n. It's given that Fourier transform of y of n is equal to y of e power j omega. From this we have to find y of e power j 0. We know that y of e power j omega can be written as sigma n y of n multiplied by e power minus j omega n. So from this we know that y of e power j0 is equal to sigma n y of n. But we know that y of n is equal to x square of n is equal to 1 by 4 whole power n. Therefore, y of e power j0 is equal to sigma n 1 by 4 whole power n is equal to 1 by 1 minus 1 by 4. This is based on the infinite series summation formula. Please note that here the summation is from 0 to infinity as y of n is a causal sequence. So upon simplification this becomes 4 by 3. From this we can say that the value of y of e power j0 is 4 by 3.